In this example, we're given the situation of a jet which is flying in a loop path. The information that we know is fairly specific in that we know the speed, we know the magnitude of acceleration, and the tangential component of acceleration when it's at point A. On the other hand, we don't really know much about the path, particularly here at A. So based on this information, though, that we do and do not have, what we want to do is find the radius of curvature of the path there at A. Well, the information that we have and the information we want to find is all really coming back to a path description, in the sense that we know the speed, rate of change of speed, and we want to find rho. That just makes sense to do it in terms of path. So on the sketch that we have, what I'm going to do is put on here our unit tangent vector, ET, which is tangent to the path there at A. We know that the unit normal, EN, as the name would imply, it's normal or perpendicular to ET. A, we're not really sure what its orientation is, so I'm just going to draw in a generic description of A. Don't be too concerned about its actual direction. But what we do know is that the projection onto ET, that's going to be the tangential component AT, which we know from class, that's the rate of change of speed, and the projection onto the unit normal EM, that's the centripetal component, which we know is v squared over rho. So in terms of the path description, we have the A, the acceleration, is rate of change of speed v dot ET. We have the centripetal component v squared over rho En. Now again, we don't know too much about the path, so we don't know the orientation of ET and E sub n. But what we can do is take advantage of what we do know, and that's the magnitude of A. So if I take the magnitude squared of both sides of this equation, I get v dot squared plus v squared over rho quantity squared, like this. And from this, I can get an expression for rho. So if I solve this for rho, I get the square of the speed v on the top. I get the square root of the magnitude of A squared minus the square of the rate of change of speed v dot there on the bottom. And with this equation, we have everything that we need. For example, the speed v, that's given to us as being 800 kilometers per hour. Well, we'll probably want to convert that to meters and seconds. So we know 1 hour is 3,600 seconds. We know that there's 1,000 meters in a kilometer. So what this is going to do is give us the speed in terms of meters per second. V dot, that's our rate of change of speed. That's given to us in some sort of odd units here. That's 20 kilometers per hour per second. Okay, so we'll need to convert that set of that kilometers to a meter. So we multiply it by 1,000. We divide by 3,600 to convert our hours to seconds, like this. So in the end, we're going to have v dot in terms of meters per second squared, and that's what we need. Magnitude of A, that is given to us in yet another way in terms of G's, 3 G's. So the 1 G we know in metric is 9.806. So if we multiply that by 3, we get the magnitude of A in terms of meters per second squared. So that's it. So the key part of this question was recognizing what we know and what we're asked to find. All of those are given to us in terms of path. Let's take advantage of what we do know, and that is the magnitude of A, Got that there on the left-hand side. We know the rate of change of speed, v dot. Up here on the top, we have v, which we know. And from that one equation, we were able to find rho. And keep in mind that we were able to get this information without knowing much about the path there at all. We don't really know its shape. We don't know the size or anything else. But just from those three pieces of information, we're able to get the radius of curvature of the path.